Welcome to qnawire.
Okay, so we're doing chapter 34, problem 27 here. And it says an insect of 3.7 millimeters tall, 3.75 millimeters tall, is placed 22.5 centimeters to the left of a thin planoconvex lens. So that means that it's going to be our object distance. And the left surface of this lens is flat. So a flat lens has a radius of curvature of infinity. And it says the right surface has a radius of curvature of 13 centimeters. Cool. 13 centimeters. Now, to think about this though, this is the right plane lens and it's planoconvex. So that means this is going to be defined as a negative with our usual sign convention. And the last thing it tells us is the index of refraction of the lens material is 1.7. Okay. So for part A, it says calculate the location and size of the image of this lens forms of the insect. Is it real, virtual, erect, or inverted? Okay, so let's write out part A here. To start, we're going to need to use the lens maker equation. So to do this, we have 1 over f equals n minus 1, and then 1 minus r1 minus 1 over r2. Cool. So let's use this equation to figure out the focal length of our lens. Now, the first R1 is always the first interface we're entering, and that's the left side, and it already said the left side is flat. So we know that this is 1.7 minus 1. So R1 is our left, which is infinity, and now we have minus 1 over negative 13. Cool. So if we plug that in, we should see that our focal length here comes out to being 18.6 centimeters. Awesome. And these negatives are canceled out, so we have a positive focal length, which is good to know. So now we can plug this into our thin lens equation that we've used many, many times here, and we can just rearrange for the value we are trying to get. We know S, so we're trying to get S prime. So let's rearrange this equation first, and we see that S prime is equal to, oops, that's too far up, SF over S minus F. So now we can just plug in this stuff, times 18.6 all over 22.5 minus 18.6. And this comes out to being 107, oops, that's a 6, not a 7. So 107 centimeters is our image distance. Cool. So this is a positive image distance. We can then find the magnification by negative S prime over S. And this comes out to being negative 107 over 22.5. So this is negative 4.76. Okay, so we know the image is inverted because it's a negative magnification, but let's go ahead and figure out what the height is going to be from this equation. And this comes out to being negative 4.76 times times the height, which is 3.75 millimeters. That comes out to being negative 17.8 millimeters. So that means the image is 107 meters to the right of the lens, and it is 17.8 millimeters tall. It is real because it's on the right of the lens, and it is inverted. Cool. So that was all they wanted for part A. So now let's move on to part B here. It says do the same thing, but if the lens was reversed. That means rearrange our left and right, or 1 and 2 radius of curvatures. So let's go ahead and see what that gives us in our lens maker equation here. So this is 1.7 minus 1. And now our R1 is negative 13. Oh, sorry, it's flipped. The ends is flip-flopped, right? So that means the convexity also flips. So this is positive 13. And now the flat side is still infinity. Cool. But this goes to 0, and we should see that this is 0.7 over 13, which was exactly what we had before, 18.6 centimeters. Now, if the focal length is the same, exactly, nothing about the image is going to be different. So that means the image is same. It's the same when we reverse these lenses. Cool. That's everything.